So as promised, this is going to be maybe a bit of a lighter weight talk, suitable for after dinner and maybe the end of a long day with lots of big, hairy, hard systems being thrown at you. This is about a programming model that doesn't amount to much. It was motivated by my working with a physicist at Argonne, and the goal of this was to do something as simple as possible that would be useful for him, and he was doing very, very large-scale computations that were threatening to, the complexity of it was threatening to get out of hand, and so we needed to make something more scalable but simpler in terms of how to use. So the thing that we gave up was general purposeness. That is, you might not want to use this for anything, for everything. It turned out to be more useful than we thought. So that is what makes it worth possibly thinking about for a bit. So we might start by thinking of, you've already been exposed to this idea. At a very high level, I think of there as being two different approaches to parallel algorithms, although sometimes these are mixed. Data parallelism, which arises from physics problems and some mathematical matrix problems, in which parallelism arises from the fact that physics is very local. You're doing the same operations on different patches of the world or the molecule or the whatever it is that you're working on. And there has to be communication to get from one patch to the next patch. And sometimes you need global operations, and sometimes you need load balancing. I'm going to contrast, so that's not what this is about. And contrast that with task parallelism, in which the work to be done is a bunch of more or less independent tasks that may not need to communicate with each other at all, such as in the case of the talk we just heard, or maybe a little bit. We have to manage the dependencies among these tasks. Traditionally, it uses some sort of scheduling mechanism that one process does for managing these dependencies. And load balancing is completely fundamental because these tasks may not be related in size or duration. So what I mean by load balancing is the assignment, that is the scheduling of a bunch of tasks. Task consists of code plus the data for the code to work on, so as to minimize the idle times of other processes. And we think of there as being two kinds of load balancing. Static load balancing, which is often the case for these, for the models in which, for the data-dependent models. So it's static in the sense that we know what we have to do ahead of time, and we pre-assign that work to certain processes. And this works well if the tasks, such as some sort of grid computation, all take the same amount of time and doesn't require any particular overriding coordination process. So dynamic load balancing, which is a very old idea, and I'm going to talk first about the old-fashioned version, is that tasks get assigned to worker processes by some master process or manager process. This used to be called master-slave programs. Now they're called manager-worker programs. And when a worker process becomes available, then it asks for more work, and the master gives it to him. So we communicate between the manager and the worker processes. Tasks might be able to create more tasks, and the tasks might be quite different from one another. So it looks something like this. This is a generic manager-worker algorithm. You have a manager process, a bunch of workers. You have a work queue that the manager knows about. It's easy to implement this in MPI, and it solves some problems. It implements dynamic load balancing because if one of these workers has a task that takes 100 times longer than the tasks working on the other, being worked on by the other workers, it just takes that long. So we get automatic dynamic load balancing in this simple model. Manager can tell when there's no more work to do. It's easy for one task to tell the manager to create more work and put it in the work queue. And it's easy for the manager to keep track of the dependencies between the tasks. Its big problem is in scalability. The manager can become a communication bottleneck if there are, let's say, 100,000 of these workers communicating with one manager and the tasks are on the order of milliseconds. He's not going to be able to manage it. And we also have a memory problem if the manager is the only one who knows where the tasks are. So the idea is to keep the good aspects of this model and solve the bad aspects. So the ADLB Idea, ADLB stands for Asynchronous Dynamic Load Balancing, is to do away with the master. Instead, workers are going to make calls to this ADLB library, and it'll be a very small API that they use. And those subroutines are going to access local and remote data. When it's remote, it'll be via something like MPI, but the MPI aspect will be invisible to the programmer. So we'll use a simple put-get interface. We can put things in the work pool, and we can get them out. So in some sense, this is a two-function API. So the manager has gone away. The workers now put things in the work queue, and when they are finished with their task that they're working on, they get a new one. And what's nice about this is it doesn't really change the algorithms in the algorithm in the workers. The worker used to send a message to the manager saying, I'm done, and the manager would send him back something, but that's just putting and getting. We don't need this manager process to exist at all. So this isn't really a new idea. Linda was an old programming system that had something like this. So the tricky bit is a scalable, portable, and distributed implementation of this work queue so that these put and get operations can find the work they need. And we're going to need a little extra sauce on these put and get operations so that to make this usable for implementing relatively complex applications. So here is all of the API for this simple programming model. It has some sort of junk that you would expect, initialize and finalize and so forth. But what really matters is the put and the get. And the get is done in two parts. First, we reserve a bit of work. We find out, we get something back that tells us how big it is so that we can allocate some memory and then get the stuff that we reserved. So we're not going to study this too hard, but the put and the reserve do have a couple of extra attributes that we can attach to these work units, and we'll see how those are used. Work units have type. They can be optionally assigned priorities. They amount to just a bunch of bytes, so there's a buffer and its length get passed. And you can say that you only want some specific target rank to be able to get this. It's a way of sending a message to someone. And you can also ask that when the when this work unit is completed, that the result be sent to a specific other rank. So this is the put, and these two things are the get, and they are the only things that really matter. Everything else is just a little bit of management. But altogether, there are really only 10 functions in the API. So this is just a few details. We can use these types and the anchor and the answer rank and so forth to set up some common patterns that we might otherwise have in our programs, like loops and decomposing tasks, sending messages and so forth. Maybe these higher level patterns could be built into the API, but they aren't. When you get back, when you ask for something, you can get various return codes that tell you the type of the thing you got, of course. Someone can say, okay, I found what you're looking for, everybody should quit. We can get back a return code that says everything's been done. So various types of things like that. So if you default most of the parameters, which you can do, this is just a very simple high-level work stealing API. There's a queue of work that the programmer doesn't manage. ADLB manages this queue. Programmer just puts things in the queue and gets them out. So, but we can we can use this to implement a number of elaborate patterns, and that's where this has turned out to be more useful than we originally thought. One way it's used is in a parallel language called Swift, which is done for writing parallel workflows. Its execution engine, this is a completely different group, uses ADLB as an adjunct, as the sort of the runtime system of the Swift compiler. We've implemented it in a couple of wildly different ways. The one that we are using at the moment looks something like this. We divide all the MPI processes in the application to application processes and ADLB servers. So each application process, we sometimes call these clients, has a server that it talks to. And so it does puts and gets to one single process all the time. And the work queue is distributed around in these servers, and they keep each other informed of what part of the data that they have. The complexity is trying to keep this synchronized, especially when there may be thousands of servers, not just 5, that are keeping this virtually shared work queue up to date. ADLB itself is simple, but it uses a lot of the non-standard stuff in MPI. So just connecting this for a moment to the MPI part of our course. The way it works is that ADLB, when you call ADLB init, it chops off a couple of processes to serve as the servers and gives the application back a communicator. So the use of MPI communicators is fundamental. The servers are in an MPI iProbe loop, so they are always waiting to get messages. They use non-blocking sends and receives. They maintain a queue of MPI requests, which they keep poking with test, so they don't ever wait, but every time through their loop, they test everything to move communications along. And we use the MPI rsend, as I mentioned in the talk on Tuesday. And since it's built on MPI, it runs on virtually anything. I debugged this on my laptop, and my physicist friend runs it on Mira with very large numbers of processes. So now I want to do some examples. As everyone else who has given you a programming model has done some simple examples, I thought I would not compute pi. It seems to me you should know what pi is by now. For those who never got anything to run, I'll tell you, it's 3.141. Anyway, so let's do a Sudoku solver, a simple physics application, a batch scheduler for clusters, and then we'll just touch on this motivating application, which is pretty complicated. So does everybody know how to play Sudoku, this puzzle? The idea is every day in the paper they publish something that looks like this, and your goal is to fill in the blank square so that every row and every column and every one of these boxes has all the digits from 1 to 9. And sometimes this is easy and sometimes it's hard. Actually, I didn't ever pay any attention to this until I thought this might be a good example for giving tutorials on ADLB, and then I became completely addicted. Anyway, this is not a good way to do this, but it makes a good example. So here's how we would write a parallel Sudoku solver in ADLB. And it all fits on one slide. So we're going to think of a work unit as one of these things partially completed. And here's all it takes to make this work. So all the processes, all the application processes execute this code. So the first rank reads the newspaper and gets the board that you're going to make as the problem and puts it in the ADLB work queue. Then everybody does a get. By that I mean a reserve plus a get. So of course, right at the beginning, only one guy is going to succeed. The other guys will be waiting for more stuff to show up. the get is, there's both a blocking and non-blocking reserve. I'll use the blocking one here. So then everybody has this while loop. So if there wasn't one, then we're all done. I'll come back to this spot. This OOH means optional optimization here. So let's skip that for the time being. So we find the first blank square. If there isn't one, then we're done. Okay, so print the solution, do a set done, and that will spread the information to all the other processes. There's time to quit. Otherwise, we check to see for each valid value that could conceivably go in there. So here's our first blank square, and we see immediately that it can't be a 1 or a 2 or a 3 or a 9 or a 7 or a 9 or a 5 or a 1 or a 7, but there are a couple of possibilities. So for each one of those, we set the blank square, we copy the board, we set the blank square to that value and put in a new board. So sometimes, in fact, a lot of the time, one work unit creates a bunch of more work units. In fact, here's a picture of how it goes. So we have, there's the blank square at the top, and the three possibilities are 4, 6, and 8. So we make new boards with 4 there, 6 there, and 8 there, and put those all in, and then we go, everybody starts getting these boards. They all get different ones. They fill them in, and you keep going until you eventually are going to fill this. You can see that you are eventually going to solve this puzzle if it's solvable, because you're going to try everything. And you can optimize in this framework. So we could do something fancy at the OOH place to fill in more squares so that we don't actually try every single thing. But even so, if you were to run this, you would be surprised at how fast you get lots and lots of work units in there. Millions, very fast. And you can use priorities to address this problem. This is a trick that helps a lot. If you set the priority to the number of filled in squares when you do the put, so what are you doing? You're saying, work first on the ones that have the fewest blanks left. So what that's going to do is start trimming down the search just the way you would do it if you were doing it by hand. And when we're all done, so we either do a set done or exhaustion will be detected if maybe there's no solution or there's more than one solution, which there isn't supposed to be. Here's what's interesting about this. These were guys in the next office from the physicists I was working with. They have a parameter sweep type of application. So it's very, very simple. They're looking for a material. They want to test materials that are defined by some 50 different parameters. So they have a gazillion different combinations of these parameters. They want to perform some computation on each combination of those and pick out the best materials for this solar cell stuff that they're doing. So it's absolutely embarrassingly parallel. I've heard people say they don't like the word embarrassingly parallel because they don't like to be embarrassed. So I've heard it called pleasantly parallel. So these things are absolutely independent. So it's the simplest possible program to parallelize. You just have a bunch of sequential programs. But what was kind of interesting about it is that they were then able to run on very large parallel machines and do many of these at the same time. And they never learned any parallel programming at all, except ADLB. So they never learned any MPI or OpenMP or anything like that. And they use this all the time, and they're quite happy about it. Here's the world's simplest job scheduler, which is useful for Linux clusters. Suppose you have a bunch of really separate jobs. That is, each one is identified by, say, a Linux command line. Then one process can just read this file, dump all the command lines into the work queue. Some of them take 1 second, some of them take 3 days. Doesn't matter. ADLB will balance them across however many processes you gave it. And it's easy to add priority consideration. So the way this works is ADLB just, one guy puts them all in, or you could stream them in as jobs are submitted, and everybody else pulls them out. They pull out a command line, and just executes the system call on that command line. So there's absolutely nothing to this, but some people find it a very handy tool. The motivating application was a function in nuclear theory research. There's a program at Argonne called GFMC, Green's Function Monte Carlo, which is considered by the nuclear physics community the sort of the gold standard for this particular type of calculation. And this program's been around a long time. It has a very had a very non-trivial manager-worker algorithm, sorted work types and priorities and dynamic work creation and all sorts of hairy stuff. When I got involved with this guy, it had scaled to about 2,000 processes on our blue gene, but he needed to get to tens of thousands of processes to get to the computation that he wanted to do, which was about carbon-12. And the algorithm needed to be greatly more parallel. That is, the work units that he was using had to be decomposed a lot, so there would be lots more work units, much more complex code. Load balancing would get totally out of hand. And so he and I started working together, and ADLB came into existence. Scalability has been a multi-step process over the years. Originally, the idea was just to balance processing time in the standard manager-worker scheme. It turned out to be that that wasn't enough. Pretty soon we had to introduce some complexity to balance memory usage. I'll talk a little bit more about that later. And then finally balancing communication as some servers started to become hotspots and so forth. But all of that was done by fiddling with ADLB, which actually is not a very big code, rather than the application, which is a very big code. Now he runs this with hundreds of thousands of processes, and it's working pretty well. This is a fairly recent performance graph doing weak scaling. So it runs up to 262,000 MPI ranks. We talked earlier about, it's a hybrid code, so it uses OpenMP to parallelize the working on a single work unit. We talked earlier about how it's sometimes difficult to know how to split the MPI processes and the number of threads and so forth. By experiment, he just determined that this works best on Mira, which has 16 cores, each one 4-way hyper-threaded per node at 8 MPI ranks per node, but 7 OpenMP threads per rank, rather than 8, which you might think. You can get ADLB from this website. Of course, these slides are available, so you don't need to write this down. Pretty handy bunch of stuff. Just check it out. You get the source code, everything you need to build it. You get the Sudoku example, so you can run it every morning when you get your paper. You get the batcher. You get the traveling salesman problem is a classic computer science problem that can be solved in a way a little bit like the Sudoku problem, but it illustrates the use of priorities and work types and so forth much more. Here's a result of a salesman visiting 13,000 US cities, and you can see with a certain level of population, and you can sort of see the density of population thus. So up until a couple months ago, this was the last slide, but we're starting to have a problem because as we're going up into larger nuclei, his work units are getting bigger. And so we're running out of memory. So let me remind you how this works. All the memory for the work units is stored in the servers, and at least in the case of this application, there's plenty of memory left over in the clients, which is sort of being wasted. And he needs to add servers, not in order to be able to manage the algorithm of the load balancing, but in order to store the work units. And so the more servers you have, the less computing power you have for work, so it's not going in the right direction. So rather than completely overhaul ADLB, we designed another very simple library, possibly even simpler, and it's a library for distributed memory management for large things. maybe some of you are familiar with Memcache. It's a very fancy distributed memory system optimized for small work units. And it's, I don't know, 40,000 lines of code, has 30 developers on its web page. Contrast this with this, it has about 800 lines of code, one developer. The way this works is if you have a block of memory, you put it into DMEM and you get back a handle, which is just a couple of long integers. And then you can get it back, you can copy it, you can free it, you can get pieces of it. And then what happens, and the way we do this is it runs as a separate thread along with the client application. So it runs on all the client nodes. The put and copy operations are local if they can be. And then what happens is ADLB just manages the handles. It doesn't have to move these work units around. It just moves the handles around. So you ask for work, you get something to do, and a DMEM handle to the data to do that. So that lets us collapse the number of servers because we don't need them for the memory. So we get more memory out of the clients and we get more processing power out of the clients. So everything is going in the right direction by just introducing this orthogonal library instead of trying to fix the central thing. Looking ahead, the object size here is an MPI int, which is always a 64-bit integer. So again, it has almost nothing to its API, just the operations I talked about. It also, like ADLB, has a Fortran interface. I always believe that if you write a library, there should be both C and Fortran versions. Okay, so what I'm trying to get across here is can be great benefits to limiting the generality of approach to solve the problem that you want. You can get scalability by simplifying things sometimes instead of making them more complicated. ADLB might be handy, if you think it might be. You have the website. DMEM is an even smaller thing that really accelerates the productivity of ADLB and might be handy in its own right. And that's all. Questions?
Just now you mentioned that if you have so the heavier items, then the work is more heavy because you have more electrons. So it's about Monte Carlo method.
Well, this is nuclear theory, so we don't know anything about electrons. But the more protons and neutrons you have, the larger these objects become. Now, the objects are not the nucleons themselves. They're Monte Carlo paths.
So you mentioned that for DMEM you dedicate a thread on the worker. Is that handled with OpenMP too?
Pardon me?
Is that handled with OpenMP?
No, that's a pthread. It's just a pthread create. And that it lives alongside the OpenMP threads that are doing the work, and that works fine.
I was just wondering how would you do it with OpenMP?
No.
It sounds like a daunting task with OpenMP.
No. OpenMP is too hard for me. Pthread create is so easy. Okay?
So ADLB is actually the figure that you show?
Well, that's one implementation. We have tried a couple of different research implementations trying to change the architecture. We built one entirely with threads. Didn't work so well. We did one based on one-sided operations. We were able to experiment with all these without changing the physics application, of course, which was nice. But we haven't found anything that works better than this separation into the small number of servers and large number of clients. And the problems that we were originally trying to work on with that, we think we have solved by splitting off the memory management part into this DMEM.
Internally in ADLB, it's essentially, let's say in that figure, 5 masters, those are communicating with each other. Are there different models inside, or is it typically more masters which communicate about the job?
So if you want to call those the masters, I call them the servers, which is the opposite, sort In that implementation of the ADLB API, yes, those are single-threaded processes. We haven't found a good way to multi-thread those to speed them up. But ADLB itself is just the API. I'm not dedicated to the particular implementation.
And the number of those, is it internally decided by ADLB?
No. Depending on what kind of work units you have, the split between clients and servers can be quite different. So unfortunately, you sort of have to determine that by experimentation. So in the batcher, for example, you'd have to go a long ways before you'd need more than one server. Steve Piper, my collaborator, has settled on about 10% as his 10% servers, as seems to work out pretty well for his application, but it could be different.
I forget if you said this, but for I/O, so you could have the servers do all the I/O. Is that right?
I guess you could. Right. This is completely orthogonal to I/O. In this particular application, the I/O consists of the energy, the ground state energy of the nucleus that you're working on. It consists of one floating point number. So I/O is not a hard part of this. But actually, he writes log files from all the clients, but this doesn't have anything to do with the I/O part.
For example, I have an application where I have something similar, and we do parallel I/O into HDF5 files, but well, actually, for right now, we're just doing it from the server essentially. But it'd be nice.
But you could do it from the clients. I mean, there's a communicator there, and that's what you need to pass to HDF5. Okay. Oh, one more.
Maybe I missed your point. I'm not sure if you do Hello Exchange or something. How can you do that?
It would be a really terrible way to do Halo Exchange. I imagine you could cram that into this model, but I wouldn't. And that's exactly why I said at the beginning, give up generality. If you're not going to do Halo Exchange, then you don't have to solve the problem of how to do Halo Exchange efficiently. I think you could probably force it into this model, but it would really be icky. I think I'd have to put a work unit in for each Halo piece. Awful.